Maxwell's equations, terms and definitions. This is a first in a series of small lectures to explain Maxwell's equations. And in teaching Maxwell's equations, it's best to know Maxwell's equations before they're taught to you. So that creates quite a challenge for teaching them. And this is why in this short series of lectures, you'll see things discussed multiple times. And I'm trying to make these different connections by explaining things multiple times. In this short lecture, my entire goal is simply to explain the terms that appear in Maxwell's equations and their units, and to try to give you a physical, intuitive feel about what those terms mean. Now, certainly we'll be discussing some of the theory behind Maxwell's equations to understand those, but the goal here is just to understand the terms. The equations themselves will be explained in following lectures. So let's get right into this. When I think of Maxwell's equations, I tend to think of them as a quad chart, 4 main forms. We start with the time domain integral form because this is the most general form of the equations. When we have differential equations, for example, those derivatives explode at interfaces where things have step discontinuities, and that means then we also need boundary conditions and other things. So the integral equations tend to be the most general, and so we'll definitely start there. But they're also the most difficult to use and the least commonly used in my experience. We can Fourier transform the time parameter and then express Maxwell's equations in the frequency domain form, or when the fields are oscillating in a time harmonic sense. And it's just a Fourier transform. Again, being integral equations, I don't see these as much. When I do see them, it's usually when derivations are starting with the equations in integral form. We will use these to derive boundary conditions, for example. We can convert our integral equations into differential equations. We'll definitely be doing that. And Maxwell's equations now look much simpler. They're in time domain form here, but also differential form. We can take that differential form, Fourier transform the time parameter, and then we get to Maxwell's equations in the frequency domain differential form. And this is definitely the most common way you will see Maxwell's equations expressed. But I think it's important to think of these in this quad chart because we can express them in any one of these different ways, and we'll choose whatever happens to be most convenient for the problem. There are other ways to express Maxwell's equations. There's Maxwell's equations that account for relativity, Maxwell's equations that account for moving media, and a variety of other things. But the 4 forms here is what you'll use most, and definitely in the lower right quadrant is what we'll use most in this class. Now, if we stare at Maxwell's equations long enough, we might ask the question, where do the material properties emerge here? We need to know those to understand how waves interact with materials. And it turns out that Maxwell's equations don't directly tell us how the fields interact with materials. Those come from the constitutive relations. So maybe you could win a bet sometime with a buddy and say, hey, Maxwell's equations does not tell us how the fields interact with the materials. Not directly anyway. And so we need this in combination with the constitutive relations to predict everything about waves. Some notes about Maxwell's equations. So as I mentioned in the last slide, the time domain integral form is the most general, but the most difficult to work with. So the frequency domain differential form is much easier to work with, and I think is why you see this form the most. I'll also point out that Maxwell's equations themselves are rarely useful. I don't wake up with some new electromagnetic idea, plug numbers into Maxwell's equations and get the answer. It does not work that way. Instead, I will plug those numbers into equations that were derived from Maxwell's equations. And very often those equations are many steps away from Maxwell's equations. but it is interesting to know that they all start at Maxwell's equations. And also, we talked about this on the last slide, but Maxwell's equations don't directly tell us how the fields interact with materials. This information really comes from the constitutive relations, and the magic is the combination of the two, Maxwell's equations with the constitutive relations, that tells us everything we need to know. From the constitutive relations and from Maxwell's equations, we can see that the electric fields, there's no terms that contain electric fields and the permeability term. So I would say that the electric fields don't directly experience permeability. Now, the electric fields are coupled to the magnetic fields, and the magnetic fields directly experience permeability. So there is an effect on the electric field, but it's an indirect effect, and I think this is a useful way to think. Likewise, the magnetic fields don't directly experience the permittivity. The magnetic fields are coupled to the electric fields, and the electric fields do experience permittivity directly. So there's still an effect on the magnetic fields, but it's indirect. Okay, on to the terms and definitions. When it comes to electric energy, I like to argue it this way. We can have electric energy or an electric phenomenon in one of two different ways. We know that radio waves travel through outer space, and we also know that waves are composed of electric and magnetic fields. So clearly there is some form of electric energy that can exist in the vacuum of space. Let's call this the electric field intensity E. We also know that we can store electric energy in the form of displaced charge in materials. Very often capacitors are loaded with a dielectric, and that dielectric can store electric energy. We will call that the polarization of the material. Now later on when we get to waves, we'll be talking about the polarization of waves, and we'll also be using that variable P to describe that. So it's an unfortunate reuse of both the same variable and the same name, but it's very different. The polarization of a wave is something completely different that we're not talking about now. Here we're talking about there's charge displaced inside of the material, and that creates little tiny electric fields, and those little tiny electric fields have an orientation, and the overall effect is the material becoming electrically polarized. So those are our two ways to have electric energy. We can have electric energy in the vacuum of space, and we can also have electric energy in matter. So the electric field intensity, this has units of volts per meters. So this tells us that the electric field intensity is most closely associated with voltage, therefore most closely associated with electromotive force and force itself. When we start calculating the force that electric fields put on charges, we will do that through the electric field intensity E. We can also think of this as the initial push on a medium. What I'm drawing to the lower left here are atoms. And so the red circles are the nucleus, positively charged, and the gray circles are the electron clouds. The electrons are buzzing around that nucleus so fast that it really forms more clouds than discrete particles. And in their equilibrium state, the electrons essentially form these spherical clouds around the nuclei. This is a way oversimplified model, but it's going to work for us here. So right now there is no applied electric field, but let's say we apply an electric field to this. Well, the electric field puts a force on the nucleus and the electron cloud, but since the nucleus and the electron clouds have opposite charge, that force pushes them in opposite directions. So what ends up happening is the electrons spend more time on one side of the nucleus than the other. This is when we call the material polarized. When it's polarized, since the electron clouds are now spending more time on one side of the nucleus than the other, there's a little tiny electric field around that. That's an electric dipole. And just due to how the atoms are arranged at the molecular scale, it may be easy or hard to displace those electron clouds when an electric field is applied. And so we characterize this through a parameter called the electric susceptibility. It's the Greek letter chi, and I'm putting a subscript E here to indicate that's the electric susceptibility, because later on there will be a magnetic susceptibility. So we apply an E field. We have some parameter telling us how easy it is to displace fields. And then we have a constant here which gives us the same units as the material polarization, which is coulombs per meter squared. Coulombs is our unit for charge, and of course meters squared will be area. So we can calculate this electric polarization P from the electric field through this electric susceptibility term. There is a second electric field term that's called the electric flux density, and it has units of coulombs per meter squared. So think of the electric flux density as the all-inclusive term. We had these two ways that we could have electric energy. The electric flux density is the thing that accounts for both of them. We see that it includes the vacuum response of space, so it includes the electric field, the vacuum response, if you will, and how we can store electric energy in matter. If we add those together, we get our electric flux density. Now this has units of coulombs per meter squared, just like the material polarization. And so the electric field D is most closely related to charge. So when we first start talking about electric fields around charges and charge distributions, we will do that through the electric flux density. And that's very unlike what you'll find in textbooks and stuff that do that with the electric field intensity E. And that makes no sense to me, and I think that ends up becoming very confusing. The electric flux density D, also called the displacement field, is the one that's most closely related to charge, and so that's the one that we will use, and our equations will be simpler for it. We're going to repeat the same conversation we had for electric fields for magnetic fields. Just like electric fields, there are two ways that we can have magnetic energy, or two different ways that the magnetic phenomena can manifest itself. We know we can have magnetic fields in the vacuum of space because we can watch radio waves travel through space. Let's call that the magnetic field intensity H. We can also have magnetic energy stored at the molecular scale. And here's my little cartoon of circulating currents. That's the little blue bar here. And that induces a tiny magnetic field in the middle. That's our magnetic dipole. And when these align, we would call a material magnetized. And we describe that with a vector M, which is analogous to that vector P when we were talking about the electric field the electric polarization of a material. So the magnetic field intensity, H, has units of amperes per meter. So this is most closely related to current. And later on, when we talk about magnetic fields around currents, we will talk about this through the magnetic field intensity H. This is also what puts the initial torque on a material. So if we look at some materials at the molecular scale, we can think of some of these having circulating currents and inducing magnetic dipoles, and they're all in random orientations. Well, along comes a magnetic push, if you will, the magnetic field intensity, and in some materials, these magnetic dipoles will line up, and the material becomes magnetized. When this happens, we are storing magnetic energy in the matter itself. So this gives us our magnetic polarization M, and it's a measure of how much magnetic energy we're storing at the molecular scale. So we have our initial magnetic field intensity H. We now have our magnetic susceptibility chi sub M, and the M is telling us that this is for magnetic fields. This is a measure of how easily those dipoles are reoriented due to applied a magnetic field. And we multiply it by the free space permeability to finally get our magnetization M. So our magnetic field intensity H is the magnetic field in the vacuum of space, and our magnetic polarization is the magnetic energy that we can have stored in matter. Now along comes the magnetic flux density B, which has units of Tesla or Webers per meter squared. If there was such a thing as magnetic charge, it would be a Weber. So the magnetic flux is most closely related to force. And later on, when we talk about forces put on current carrying wires and loops, we will do that through the magnetic flux density B. A compass needle, for example, points in the direction of the B field. The magnetic flux density is the all-inclusive term that includes how magnetic fields manifest themselves in outer space and also in matter. So magnetic flux density is the all-inclusive term, just like the electric flux density was the all-inclusive term. There's also a J in Maxwell's equations. This is called the electric current density. It has units of amps per meter squared. And if we look at a conductor, that's what we're seeing here. If we look at a cross section, there could be current flowing in any tiny little piece of that cross section. And so we will call these little tiny pieces of current the current density. And it does not have to be uniform throughout a conductor. In the picture I'm showing here, it is uniform, and that's usually the approximation we'll make. But later on, when we study high frequencies, we'll see that there's something called the skin effect. And in fact, the current is much more intense near the outer part of the conductor. And at high frequencies, sometimes the inner part of the conductor is not used at all. So this current density does not have to be uniform. We will very often make the approximation that it is. So anytime we have a term that has density in it, there's usually an integral hiding behind it that we can integrate that density term to get the total term. And that's what's happening here. We have our current density. We have it dot producted, if you will, with our differential surface. So we are integrating the component of current that is punching straight out. And so the reason for this dot product, if any components of the current are traveling transverse, they are really not contributing to current flowing along the conductor. But anyway, if we add up this current flux, if you will, we get total current I. But the J is the term that appears in Maxwell's equations. We have the volume charge density. That's rho sub V, the V meaning it's a volumetric term. It's the volume charge density. This has units of coulombs per cubic meter. Coulombs is charge, and of course a cubic meter is volume. How much charge per volume? That's our volume charge density. And as I mentioned before, anytime there's a density term, there's an integral hiding behind it that can add it all up to get the total term. So that's exactly what's happening here. We have our charge density, our differential volume, and if we do a volume integral, we get total charge Q. And over to the left, this is not my best work, but I'm trying to visualize a volumetric charge where that charge density is varying as a function of position. And maybe I didn't do such a great job here, but I tried. It looks pretty ugly, I think. Now on to the constitutive relations. We have the parameters that are describing the materials themselves. And when it comes to the response of a material due to electric fields, we have the permittivity. And it's the Greek letter epsilon. It has units of farads per meter. And if you've had circuit theory before taking this class, which I'm sure you have, you'll recognize the unit farad as capacitance. And what do capacitors do? They store electric energy. And so the permittivity is really the measure of the ability of a material to store electric energy. So we will write our permittivity as the product of two terms. We have the free space permittivity, which has a value of 8.854 times 10 to the minus 12 farads per meter. This 10 to the minus 12, that's a really small number. And really what that tells us is that a farad is actually a very huge unit. Okay, back to permittivity. It's the free space permittivity, so that's the permittivity we will experience in outer space. Everything else has to have a permittivity higher than outer space. So we multiply the free space permittivity by the relative permittivity. This term has no units. The units are in the free space permittivity. So the relative permittivity, more commonly called the dielectric constant, is unitless and is greater than or equal to 1. When it's equal to 1 exactly, this means we're in the vacuum of space. Everything else has a higher relative permittivity. Plastics have a permittivity around 2.5. There's ceramics that have a relative permittivity 10 to 20. These are also much more convenient numbers to use than to express just the overall permittivity, which will always have a 10 to the minus 12 sort of factor to them. And that's just less convenient to talk about. Similarly, we have the permeability, and this has units of henries per meter. And from circuit theory, we used henries to characterize inductors. And what do inductors do? They store magnetic energy. So the permeability is a measure of how well a material stores magnetic energy. And it's most closely related to inductance. Just like the permittivity, we'll write the permeability as the product of two terms, the free space permeability and the relative permeability. And so the free space permeability is 1.256 times 10 to the minus 6 henries per meter. And everything else has to have a relative permeability higher than the vacuum of space, so this relative permeability is always greater than or equal to 1, and it has no units. There is the material conductivity, and this tells us how easy it is for an electric field or a voltage to push charge through a material. The more conductive it is, the more easy it is to push charge. Now, this picture here, the red circles are the positive charges and the blue circles are the negative charges. And of course, if you apply an electric field to this, the negative charges will travel in the opposite direction because that's the direction of the force that the electric field puts on those charges. And the positive charges will move in the same direction as the electric field. And for whatever reason, we determined that current will be in the direction of the motion of the positive charges. So in this configuration, our electric current density will be in the same direction as the electric field. And also our total current we think of being in the direction of the total electric field. But this all starts with the conductivity. Instead of conductivity, we can characterize our material in terms of the resistivity. And this is just 1 divided by the conductivity. The higher this number, the more resistive a material is to current being pushed through it due to an applied electric field. Interestingly, we have Ohm's law for electromagnetics, where we have the current density equals the conductivity times the electric field intensity. This is just like I equals V 1 over R. So in electromagnetics, this is how we write Ohm's law, and we will be using this later. And the total current is the current density times the area that we're capturing that current density through. In this case, we have this square window, that's our area S, where we have our current density, and we add all that up, we get total current. Now, this equation has an approximation built in. It approximately says that the current density is uniform throughout that cross-section. If it was not uniform, we'd have to go back to the original integral. But when it's uniform, that's how we get total current. Now we need to talk about the types of electric current. There are 3 types of electric current, and each obey different rules. The first we'll talk about is the conduction current. This is the flow of free charges through conductors. This is what we're used to from circuit theory. When we talk about electricity or electrical currents, normally we're talking about conduction currents. But there's two other types of current. There's a convection current. Well, charges can also flow through insulators. Maybe this seems counterintuitive, but maybe you've done the experiment where you blow up a balloon, you rub it on your hair, and then that sticks to the wall due to the electrostatic force. And that only happens because charges were able to flow from your hair into the balloon, and there's no conductor involved there. So charges can flow through insulators. And then last, there's this displacement current. Remember back when we talked about applying an electric field and what happens at the molecular scale, these electron clouds displace. Well, during the time, as soon as we turn on that field, there's this very short period of time where that electron cloud is in the process of displacing. And in fact, there is this net movement of charge at the molecular scale. It does not last for very long. But that net flow of charge is a current, and that is called the displacement current. So those are our three types. We can talk about the total current, and we have to add all three of these together. So our conduction current, as we mentioned before, this is the current that we dealt with in circuit theory. Current or electricity flowing through a wire is our conduction current. When we're talking about conduction current, we talk about a current density through the cross section. We add that up, we get a total current. And we also have our electromagnetic Ohm's law. J, the current density, equals conductivity times the electric field. Our convection current, and this is the flow of charges through insulators. And maybe it's counterintuitive that that can even happen. So our convection current, J with a subscript epsilon, because that's indicating we have an insulator here or a dielectric. It's our charge density times the velocity of those charges moving. And so the product of those two gives us our current density. We also have this continuity of current equation that our charges have to obey. So let's think about what this equation says. It's del dot J, this is divergence of J. So J is a field. It's our current density. And our charges can flow in different directions. So it makes sense it is a vector field. Well, del dot J, that is the divergence of that. Remember what divergence is. It is the tendency of a vector field to look as if it is emerging from a single point or converging to it. Well, if we're looking at our current, and we seem to have a whole bunch of current coming from a particular point, well, there has to be some source of charge at that point to do that. And that's what the right-hand side of the equation is saying. This rho v is telling us the charge, and the partial derivative with respect to time is telling us this amount of charge is changing with respect to time. And so that either means we're adding charge or removing it. So let's pretend we're adding charge. Well, it makes sense then that there would be this outflow of current from that point where we're adding charge. So we have the continuity of current equation. Our displacement current. So we start off at the molecular scale with our atoms, and then the electron clouds are in their equilibrium position. When we apply an electric field, it pushes the nuclei and the electron clouds in opposite direction. It stretches these electron clouds, and we get these little induced electric dipoles. Well, during that transition, there is a net flow of charge at the molecular scale, and that is a current. And so the displacement current is the change in the electric flux density. Remember, that's the all-inclusive term that include the outer space electric field plus the displaced charges, the electric polarization of the material. So anytime our D field is changing with respect to time, that gives us a displacement current. Now, clearly, this is very short-lived and probably very small, but it definitely exists. And in fact, this term is the term that Maxwell himself added to Maxwell's equations as sort of unified everything and predicted waves. So the total current is the sum of the conduction, convection, and displacement current. Now in Maxwell's equations, you will see just a J term. And in fact, the J term only includes two of the types. It includes the conduction and the convection. Now what's unique about those and different than the displacement current is these two forms of current are due to free charges. The charges are not bound to a nucleus. They're free to move around. So the J term of Maxwell's equations, we'll call that the free charge current. The displacement current, which is also very important, we write as the partial derivative of D. And this is due to bound charges. This is that little tiny current that generates in the transition as the electron clouds are either stretching the cells and pushing in a direction or relaxing back to the equilibrium state. Either way, we'll have a net flow of current. And so we don't write that as J anymore. We just write that as the partial derivative of the electric flux density with respect to time. Well, that's enough with current, and our last topic is duality. To fully illustrate duality, we'll write Maxwell's equations, but with two additional sort of fictitious terms. We know there is no such thing as magnetic charge, but we can mathematically add a magnetic charge to our two equations. So we'll have a magnetic charge density to our Gauss's law for magnetic fields, and we can add a magnetic current density to our Faraday's law. I know we haven't talked about that yet, but now Maxwell's equations look very similar. These two divergence equations look very similar. Our two curl equations look very similar. And our constitutive relations look very similar. They look similar in their mathematical form, and this is really the origin of the duality. Really, we have a set of three equations here, but that set of three equations is just copied twice and the variables are interchanged. So here's a chart of the duality. If we're looking at things from the perspective of the electric fields, we have the electric field intensity, units of volts per meter, and this is sort of our initial electric push. This is the way electric energy manifested itself in the vacuum of space. Well, on the magnetic field side, we have our magnetic field intensity, units of amps per meter. That was our outer space version of magnetic energy, and also the initial magnetic push on our matter. Then we had our all-inclusive term for the electric field, the electric flux density with units of coulombs per meter squared. Well, the all-inclusive term over here for magnetic fields is the magnetic flux density with units of Webers per meter squared. We had an electric current density, amps per meter squared. We have our magnetic current density, Webers per second meter squared. We have an electric charge density, rho, and now I'm not writing it with the V subscript, it's an E subscript, so that we remember that this is the electric charge density compared to the magnetic charge density. But since this rho m really doesn't exist, and we almost always set it to 0, then we'll put a V in here where we have an E to remind us that that's the volume charge density. And then permittivity for electric fields, permeability for magnetic fields. And Maxwell's equations really look the same. We can literally just interchange variables and we can convert one equation into the other. Almost. There is this negative sign sitting here, and that's different for the two different curl equations. And we'll talk more about that later. That has to do with handedness of the curl operation. And we'll talk about that when we get to Maxwell's equations. So why do we care about duality? Well, here's one that's not talked about, but it's something that I use extensively. When I am deriving something from Maxwell's equations, and it's new, I don't have a textbook or a paper to compare anything to, how do I know if what I've derived is correct? Well, I can derive it twice. I'll derive it once in terms of the electric fields, then I'll derive it a second time in terms of the magnetic fields, and at the end I will check, do those answers look the same just with the duality? We pull out terms on one side of the chart and put in the terms on the other side. If we can swap those terms and see the same equation again, that's a pretty good indication that my derivation is correct. Certainly if you can't do that, the derivation's wrong. So I use this all the time as a self-check. There's also a physical interpretation of this. We might have this really cool design. Maybe you're searching the literature and you see this really cool design, but it makes use of permeability. It does something really cool that you want, but you can't access a material that has that particular permeability. It turns out it's very difficult sometimes to get materials with high permeability, but it's easy to get materials with high permittivity. Well, we can just replace the permeability with permittivity. The roles of the fields also reverse themselves. Whatever the magnetic fields were doing with the permeability, well, now it's the electric fields doing that with the permittivity. But very often we can get the same sort of macroscopic behavior. Like looking at it from the outside, it'll behave the same way. If it's resonating at a certain frequency, it'll still resonate at that same frequency. It'll just be that the electric fields in the second case with permittivity now look like what the magnetic fields look like in the case with permeability. So there's some limitations maybe, but it gives us design freedom.